Welcome to our ArangoDB Hackathon submission, ArangoLens AI, an AI-powered investigative tool to analyze criminal networks and solve cases faster than ever before. Who are we? We're Nikhil and Ishwarya, software developers by day, creative explorers by night, and database tinkerers 24/7. When we first stumbled upon ArangoDB, it was love at first query. The flexibility, the power, the multi-model magic, we couldn't resist. Why are we here? When we heard about this hackathon, we tried to act normal. We really did. But the moment we saw ArangoDB and build something awesome, our self-control flew out the window. We grabbed our keyboards, fueled up on caffeine, and jumped in. Now, we're here to push the limits of what's possible with ArangoDB, have some fun, and hopefully, build something that makes you say, wait, they did what? Let us now introduce you to ArangoLens AI with our creative demonstration.
Too many leads. I need a better way.
For our project, we've chosen the Chicago Crime Records dataset. This dataset provides detailed information on crimes, including locations, types, timestamps, and individuals involved. The problem we're solving is that manual crime analysis often misses hidden networks, connections between criminals, crime patterns, and locations. Our AI-powered tool leverages LLM and the power of GraphRag along with NVIDIA-powered CUGraph to uncover these hidden links, helping solve cases faster and more efficiently. We began with pre-processing the data, installing the dependencies, downloading the data from Kaggle, sampling the dataset, and adding synthetic data for the names of criminals to make the dataset more informative. As our dataset is in CSV, there is a need to convert this data to the graph format so that we can store it in the ArangoDB. We start by installing the necessary modules. Here we are also specifying to configure Network X for GPU performance. Then we move to initializing the graph object and sampling the data frame to reduce the heavy load on database. Then we have iterated over the sampled data frame, creating nodes with critical information, all revolving around the respective crime, like the crime ID, location, criminal name. To define how these entities are related to a particular crime, we define the edges and their respective relationships. Finally, once the graph is created, we can see that there are roughly 160K nodes and 420K edges. To understand the nature of the graph, we have also performed some validations. Firstly, we have checked the number of connected components, which is 1, meaning the graph is fully connected, and this can also be validated by looking at the size of the largest node component, which is equal to the number of nodes. Then we try to check the top nodes with the highest degree of centrality, and find that those of the nodes related to crime, which does make sense. Now that we have created the graph object, it is time to persist it in the ArangoDB database to begin with the magic. As our first step, we install the required modules and import them. Then we initialize the Arango client, which will give us the database instance that we will be using to connect with the ArangoDB. Now we will be using the NX ArangoD to persist our graph object into the ArangoD. We pass on the required parameters and also specify the right batch size to meet the latency. We can see that the graph is successfully created. Then we try to get the stored graph and the number of nodes and edges clearly match with our graph. Let's see how our data looks in the amazing ArangoDB Database UI. First, we navigate to our Database UI. In the Database UI under the Collections, we can see that there are two types of collections for us, Node and Edge. To get deeper insights, let's check the node collection. We can see the number of documents match the nodes of our graph. Let's see the content of a node. For example, this JSON holds the name of one of the criminal. Not just this, let us go and explore the graph that ArangoDB has created for this data. This is the graph of roughly 10 nodes to help understand the connections. When we expand the node, we can see that more edges are added. Visualization is very important when dealing with graphs, so let's go ahead and see how a sample of our graph looks like. We have sampled 250 nodes from our graph to create a subgraph. We can see that the nodes are connected tightly, and also it is clearly visible that the graph can be easily traced. Finally, the stage is set for our LangGraph agent to take over. We start by setting up the credentials and config for our Boto 3 client, then install the important modules related to Bedrock, LangChain, and LangGraph. Don't forget to check if you're on GPU, we sure are. Then we proceed with the imports of all the necessary modules. We also have to initialize the LangChain-compatible ArangoGraph. Here we have some well-crafted prompts for graph schema and system message. Then we have initialized our Bedrock client, in which we have used Anthropic Claude 3.5 Sonnet version 2 as our LLM model. Here comes one of the most critical part, defining the tools. We have a tool to convert natural language to AQL queries, and for continuous flow, we have used ArangoGraph chain. Then we have another tool which will convert the natural language queries into Python code based on NX and ChuGraph, utilizing the power of NVIDIA GPU. The code that is generated by the LLM will be executed to get the results. We have here the list of our tools. Here we have initialized our agent using the LangGraph create_react_agent package, passing the LLM and tools in this. Then we have the method which will help in querying the agent using invoke calls.
Now we can see the big picture.
Let's break the ice and finally use what we have built. First, we will be looking at a query that results in AQL Query lookup. The query is to fetch the locations where criminal Michael Smith has committed crimes. We send the query to our agent. The agent decided that this query can be solved by AQL Query, hence entering QA chain. And here we go. The query is generated purely in AQL, and is filtering on different parameters, making it more optimized. The agent then uses these results to craft a well-formatted output. It has segregated the crimes based on the north and south sides, and has gone even further to explain the interpretations based on the resulting locations.
What about a hybrid type of query?
Our application is definitely capable of solving complex queries. Here we have a query which may result in a hybrid query execution. The query is to find the shortest path between the two mentioned criminals. The agent first decides to run the AQL query and finds the nodes of the two criminals involved. Then it uses these nodes to find the shortest path by using the capabilities of GPU-powered NX CuGraph. Once the nodes in the shortest path are found, the agent proceeds to get the information about these nodes using AQL Query. Isn't it just awesome? Then it crafts the complete details in simple language for us to interpret. It shows how both the criminals are connected to each other. Also, what could be the shortest route to reach from one to another?
Finally, what about UI?
To enhance and ease the user experience, we have used Gradio. We have created a method which will be used by the Gradio to query our agent. The query is given to find all the crimes associated with a criminal. As we can see, it is successful in finding all the crimes, also providing more insights into the same.